So, good afternoon, everyone. My name is Tereza Leonhardt, and I'm the leader of the Unicorn Club. Maybe it's the first time you've heard about us. We are a club for everyone at UCT, and what we do is mostly scientific popularization of topics throughout UCT. We also invite external speakers to give us lectures, and we do scientific communication through writing workshops and Wikipedia workshops, etc. Hopefully you will come to our other events as well. I'm very pleased that there are so many of you here. Frankly, I didn't expect that, but please feel welcome to stay after the lectures, as we have some refreshments prepared for you. The lectures will be organized in such a way that we have 4 speakers today, and they will all give us a short talk. And after their talk, you're welcome to ask them questions, and after each short block of lecture and discussion, the next speaker will come. However, if you are interested in their talks or their lives in more detail, again, please, you're welcome to stay after the lectures for the meet and greet. And now, without further ado, I would like to welcome all the members of the VS Lab. So one member is still missing. Okay, that's fine. You will see him later, okay? So this is Dr. Svoboda and his all-star team, Tereza, and Tomáš. They are a brand new laboratory at UCT. They are recipients of prestigious ECR grants, and today they will give us talks about attosecond spectroscopy with regards to chirality. So first it will be their leader, Dr. Svoboda, talking. He will tell us about how to manipulate nanostructures, molecules, and even the spin of individual electrons. But before that is possible to manipulate the molecules need to be poked and prodded. So what happens when you watch an electron? And how do you actually do that? Let's dive into the fascinating world of attosecond spectroscopy, starting with the group leader, Svoboda. A little about him. He is a UCT alumnus. After earning his PhD at ETH Zurich, he completed a postdoc in Colorado, USA, and then decided to return to UCT Prague to start his own research group, VS Lab. So please, Vít, introduce us to the relationship between lasers, molecules, and chirality.
So good afternoon, everyone. So it's really my pleasure and honor to be here to talk about something I really love to do. This is like why I came back to kind of start something new at my alma mater. So my talk is named From Laser Pulses to Enigmatic Dance of Chiral Molecules. And I will divide my talk into 3 pieces where I will introduce all these concepts to you, and hopefully at the end it will some kind of merge as jigsaw puzzles to one beautiful kind of picture, and we will be all happy and understand what my group is doing. And as all the good books, and especially the holy book, I am going to start with light. So light can be thought of as a wave. So it's a special wave which is out of 2 components. One component is an electrical wave, here in red, and one component is a magnetic wave, here in purple. And as you see, I do it properly, as almost no one does. So I multiply the strength of the magnetic field by the speed of light, because otherwise you wouldn't see the wave. This is also why usually and normally we are totally forgetting that light is out of a magnetic wave as well. Nevertheless, Because it's a wave of two components, we can call it as electromagnetic wave. And as a physicist, I really love to think in equations, so there will be a lot of equations in my talk for you to enjoy. So one of them is this one. It's a very simple one. So this says that the electric field, you see, I already forgot about the magnetic field, has to do with some periodic function, be it a cosine, and there are some constants. This one is quite simple, you already see it from the picture. It's the amplitude of the wave. So then there are two other important components which relate with the oscillation in space and time. So the K is called the angular wave number, and it tells you how many of these waves you see in one pulse or in one wave. The other one is angular frequency and tells you how periodic is the wave in time. Because we physicists, we are really, really lazy, so we simplify even this equation to something which looks like this. So we have only the amplitude, and whatever was here we call an absolute phase. And usually we are not happy with just one wave. So if we have more than one wave, so light can cause like some interference, we call it light interference. And you know that effect. So for example, this is Svoboda, where you see this beautiful pattern which is due to the interference on so-called thin layer. So how does it work? So it's pretty easy. So you have two waves, here blue and orange, which are exactly alike. So they have the same phase and they have the same amplitude. And now if they interfere, it's nothing else than adding them up. So we will get this wave, and such an addition we call constructive interference. But we can also create another possibility with light interference, which is if we will have this orange and blue waves, and they will be offsetted with respect to one another. And this offset we call phase shift. So it seems the phase is very important. And now, if and only if this phase is exactly pi, so we get out of two lights darkness. And we call it a destructive interference. So it seems that interference matters. But we like it even more because interference can generate a light pulse. How? So I will show you. So say we have a lot of waves, and we can think of a lot of waves which have different wavelengths. In other words, if it's visible light, we can think of them as colors. So here we have several waves with different colors. And please pay attention to the fact that all the maxima are kind of in phase. So phase seems to be very important. And only if all these waves will have constant phase relationship with one another, we will get the light pulse. And we can get the light pulse which might be even shorter than 30 femtoseconds in times. Really quick. And for this, very recently, there was awarded a Nobel Prize in Physics for generation of attosecond pulses. I mean, here we are even less than 1 femtosecond. And it was to pair agglutinin, Ferencz gas, and Anglia. Beautiful. So we know how to get a light pulse using waves. So if we will have another situation where all those waves are not kind of in phase, meaning the maxima are not on top of one another, so we have a random phase relation between one another, we will never ever get a light pulse. We will get some random noise. So we need to control the phase. The thing is, how to do it? So we need to fix the phase relationship between the waves. So we do it with light-matter interactions. So how exactly? So there's something which is something you all know, which is called spontaneous emission. So that's when you have some excited matter, you have some electrons in some excited states, and then suddenly they can pop down to the ground state, and they emit a light in the form of a photon. Why? Because there is a conservation of energy. If in physics you don't know, just keep in mind that conservation of energy always works. So this we call a spontaneous emission. We are also chemists, so we love equations. So here is the way how we can write it. We have excited matter, and then it de-excites, and we get some light. But this is really not useful because we can control when the photon appears. So we rather work with something which is called stimulated emission. And the difference is that we start with the excited matter, but we also have a photon. And this photon comes by and triggers this process, so that we generate at least 2 photons. Again, here is the chemical equation for such a process. But the very important thing is that these 2 photons, they will have exactly the same phase. And this is the trick we are going to harvest to construct a light pulse generator, aka laser. Laser is nothing else than light amplification by stimulated emission of radiation. If you don't believe me, bear with me, because I'm going to show you. So laser is nothing else than some laser-active medium and 2 mirrors. One which is totally reflective and one which is partially reflective. So this is where we will get our laser output. Well, very much with this laser point. So we start with some random photon which appears from somewhere, and then that one gets amplified and amplified and amplified. And then when this light hits the output coupler, some light gets out, so roughly 5 to 10%, and the rest is going to be reflected back into the active medium, we get more photons, and we started a light oscillation inside our laser. So we can think of a laser as a light resonator. So that means we would like now to know what light fits into our resonator. Not all the lights fit in. So for example, if we have two mirrors and they have a particular distance, and say we have this wave. So will that wave fit? We don't know. Will this wave fit, which is just slightly different, this delta, it's just very slight difference in the waveform. So we have to have what we call in physics boundary condition, and we require that the amplitude of the wave at the mirror is zero. Such a light will stay in our resonator. So that's the case for this orange wave. Whereas, in this case of the red light, that's not true, therefore the red light will leak out from our resonator. So it will not stay in. Therefore, we can write an equation which tells us which waves will stay in the resonator, where the m is the important parameter. So if we have m, say, equal to 1, we have a very simple long wave. Then if it's 2, we have a shorter wave. If it's 3, we have even shorter wave. So like such, we can have multitudes of waves in our resonator. That's brilliant. So can we harvest it through the interference to get the light pulse? Yes, we can. So where is our pulse? So if, again, all these waves in the laser will interfere, so this is our resonator. So an interference, as we already saw, is nothing else than just adding waves together. So we will add them up, we will hope that they will have the good phase relationship, and then we get the pulse. So now, when we have a pulse, we might ask, so is this pulse really ultra fast? It matters, right? So the pulse duration, right, is somehow related to the number of colors, wavelengths, different waves in our pulse. And there is something which is very much like uncertainty principle between time and frequency, which tells us that these two numbers are not at all independent. How it works, like such. So say, when we will be generating long pulse, this is by the way what I have here in my hand. So that means that the spectrum is very narrow. And in order for this principle to work, that means that our time profile has to be extremely broad. In our case, when we will have loads of frequencies, say spanning the whole visible frequencies of light, we will get very short pulse in time. So, in a way, to kind of get ultra short pulse, we need a lot of colors. So that basically means that in our laser, well, actually we should think of it, that what propagates is a pulse. So the pulse starts here, then gets amplified, something gets out, the rest gets back to the active medium, and again, it's a cycle. The laser light is nothing else than the runner on the wheel. And that cycle takes certain time, certain period, and at every single moment when the pulse is here, something gets out, so that's our output. So basically, every single laser generates a train of pulses. Like at one period is this one, next one, and so on. So now you might ask, so if all the lasers are pulsed, and so how come that here you see the lasers being always there? It's not continuous, right? It's not pulsed, it's continuous. So it works like such. There is a difference between continuous and pulsed lasers. And the difference is such. So if every single pulse is broader than what is the period inside the laser cavity, we generate a continuous laser. If it's that the period is much bigger, much longer than what is the duration of individual pulse, then we are getting pulse lasers. So that's how we do it. So we are ready and equipped to generate a femtosecond laser. So how we do it? So we have an oscillator, surprisingly it's not called resonator anymore, and that generates very weak but short pulse, say 30 femtoseconds. So then what we do is we send it to a pulse stretcher. Pulse stretcher really does what would you expect from the name. So it stretches the pulse, say, to 300 picoseconds, so 4 orders of magnitude, that's beautiful. So then we amplify that pulse, so we get it stronger, and then we shrink it again, so that's called pulse compressor. And pulse compressor, by the way, is nothing else than just pulse stretcher run the other way around. So, and at the end of the day, we have extremely intense, very short laser pulse. So again, for this was awarded a Nobel Prize. This whole process is called jerk pulse amplification, and it was Jean Meru and Donna Stickle. By the way, at the time she was still a PhD student, so if you come to our lot, who knows? Anyway, so let's speed things up. So can we generate like such an attosecond laser? Let's see. So let's try the naive way. That would be, we have already the femtosecond laser, say 30 femtosecond pulse, and we would get something what I would call attosecond pulse compressor. And we will hope that it shrinks our pulse below the 1 femtosecond barrier, the magical barrier. So, can we really do it? Maybe. Because we have to ask what color is such a pulse which is, say, 20 femtosecond long. So, again, in pictorial way, so what I'm asking is, like, how long is this pulse? Or, in other words, I know how long is this pulse, it's 20 femtoseconds, and I'm asking, what is this central frequency? And that's a very simple calculation. If I plug in the speed of light and this pulse duration, I get the central wavelength being 6 nanometers. And the problem with 6 nanometers, right, it lives in the X-ray regime. And there is no material to reflect anything at 6 nanometers. So, meaning we don't have any available laser medium for such a pulse. So, this is not the way. We must figure out something else. So, how we are going to do it? So, in order to get an attosecond pulse, we will again use the light-matter interactions. So, how we do it? So, we have a nozzle with a high pressure of some gas. And again, I am a very poor chemist, so I work with a simple gas, such as argon gas. So, those are just balls, right? So, we have the expansion of those balls into a vacuum. So now what we do, we come in with 30 femtosecond pulse. And here I just stretch it because, you know, in time it's a really long period compared to 20 attoseconds, right? And then only if the pulse is very strong, meaning we are very close to the maximum of that oscillation of the laser field, we generate an electron, a free electron. We ionize the ball. And that ball is then driven as a surfer by the wave on the ocean. So here, the surfer is the electron, the wave is our electric field, and it's driven around. And by doing so, it gets an energy. And then what can happen when the oscillation swings, meaning when we are going from top to down, and here from down to top, the electron is kind of carried by the wave back to the parent ion, and it can recombine. And that recombination generates the burst of attosecond pulse. So if we now look into this process in more detail, so we can zoom in, and it looks like such. We have the atomic potential, which will be coulombic, but we have such a strong laser field that it bends it. Then the electron can tunnel through. Then it's propagating by this field, and it's gaining energy. And at the end of the day, there is another band. It can recombine and generate this burst. This is called three-step model. This is what can get you a Nobel Prize. So by doing so, I finished the first part of my talk, the laser pulses. So in other words, we need an interference, we need many ways. We need to fix their phases, and then if we are lucky, we might get a short pulse. So this is what we really do. Right? Short pulse. So now, I would like to talk about motion. So I'm going to get into this dance part. So what is motion? So motion, for physicists, is nothing else than a sequence of positions at different times. And generally in physics, we like to call some things, so we call it trajectory. Right? And a very simple example might be, this is a cannonball, and say we would like to shoot the target, and we have some obstacles, so we have to shoot above the target, right? So how to do it? So we basically wanted to generate this trajectory, and in such a simple example, we can really calculate, we can just do a theoretical experiment, like thought experiment, as Einstein said once. So, how to do it? So, we need to find the trajectory, and it's always good to start with Newton's second law of motion, right? Where the total force is just mass times acceleration. So, as a physicist, we love to have our coordinate system, so say horizontal direction will be x, and vertical will be y. Then we have to realize that we are on Earth, so whenever the cannonball is in flight, so there is a gravitational force pulling it back to Earth. And then we also have some initial velocity, like imprinted onto the cannonball by the cannon. And as you see, because we wanted to avoid the obstacle, so we have to have there some elevation on the alpha. Then we do what you probably heard during physics lectures, that we kind of split into the coordinates, and we do so simply because it's easier to solve this problem one by one. So first we start with the x direction. There we don't have any overall force, so it's very simple. We just integrate once, we integrate twice, and here is the result. So in the y direction it's a bit more complex, but here is the famous trick, like when something is free falling, it doesn't depend on the mass of the object, right? Integrate once, integrate twice, and we have the result. So now, what we would like to do as a physicist, let's do an experiment. So are you ready for that experiment? So 3, 2, 1, go. And we hit the target. Excellent. So, but not always the physics is this simple, right? We might be interested in complex motion, such as this one, where we have a guy on a skateboard doing some very cool fancy tricks. So we will never ever be able to figure out all the equation of motion for this, so we have to do it differently. And the way we do it, we will take some very fast camera. And the fast camera will do one thing to our motion. It will split it into a sequence of pictures. And how far apart are individual pictures in time, we will call as a time resolution. That's pretty good and tool, but no theory, only experiment. So how to do it? So again, I will start with history. So let's start with the history of ultra-fast motion. And apparently it seems that at the end of the 19th century, people were extremely interested whether when horse is galloping, if there is a moment when all the legs of the horse are above the ground. So they set up such a special kind of horse, this one, on a track, which was equipped with those tripwires which triggered sets of cameras. The pictures back then looked something like such. They had a rig of 24 cameras connected to those 24 wires, and then they did and repeated this experiment for, I don't know, 4 months long to kind of get those pictures. So, you know, at the end of the 19th century. But at the end of the day, they get something really interesting. So they get pictures which looks like such. And as you see here, it seems that the horse is flying, right? All the legs are off the ground. So with this very elaborate experimental technique, they managed to kind of have a resolution of 60 frames per second, so time resolution roughly of 16 milliseconds. Not spectacular, but not bad for the year 1878, right? At the end of the 19th century. So nowadays, the state-of-the-art cameras are far, far better. So for example, this one, which is one of the best currently, which is some special CMOS type camera, which can collect 2.5 million frames per second, or in other words, a resolution of 0.4 microsecond. And now you might ask, is it good enough for us as chemists? And I'm going to show you. So, is it fast enough for molecules? So molecules can do a lot of motion. So for example, they can translate. So for example, now I can translate such that those guys can see what I'm saying. So this is a translation motion, and molecules do it really fast, roughly. It's a bit longer than 100 nanoseconds. So then molecule can rotate. I can also show that. Right? This is a rotation. I cannot do it that fast, but molecules can. And the rotation are typically on the order of 100 femtoseconds to 100 picoseconds. They can even vibrate. I can also do that. This is this. Right? It's kind of like a stretching, and that's really, really fast motion, something between 8 to 100 femtoseconds. And the fastest motion molecules can do is electron motion, which is much faster than a femtosecond. So we have to have the attosecond pulses for those. So that means even the fastest camera nowadays is not even near to slowest translation. So what we are going to do? So molecules really move fast. That's the sad story. So it's moving that fast that even the fastest electron, which is probably the CPU in your computer, cannot like keep up with molecules. Currently the fastest are somewhere around, you know, picoseconds. So, but optics can, and it's thanks to several discoveries. So first one is in 1961, which is the year when my man developed the first laser. Then 4 years later, there was first active mode locking. This is other like very complex word for saying we want fixed phase. Then later on, and exactly the year I was born, the diode sapphire laser was developed, which is currently the workhorse of ultra-fast community. So good year to do ultra-fast. And here, this is the HHE. This is the 3 steps I was describing to you how to get the attosecond pulse. So, as you see, the result of all those developments is that currently the optics is at least 1,000 times better in time than the fastest electronics. That means that this camera, forget it, too slow for almost everything. Electronics may be good enough for some rotation, but definitely not for vibration and for sure not for electronic motion. So, what we have to do is to build a photon camera. So how to do it? So we will take 2 pulses. One which I will call pump pulse and one which I will call probe pulse. If I would like to give you an analogy with a classical camera, it means nothing else that the pump just triggers something and the probe just takes a picture of them. So that means something like such. We will take this pulse, we will send it through some like focusing lens to our sample. Then later on we will come with the probe pulse, which say we send through a different distance and we get the picture of that. Say that picture is some signal we would like to have, which will hit which is hit by our detector, and then what we have is our first point of our first signal. This is this blue crossing here. But that's pretty sad, right? Because we have only one point in time, so not so much of the dance of molecules, right? So how to do it better? We can introduce a delay and using the fact that the speed of light is constant, so meaning the change in position is a change in the time. So like such, if you set it into a motion, we can get more and more points. And then we can just spin it. And here, this is our time resolved signal capturing the dynamical motion of our molecule. And this experiment is called pump probe. So, with this, I'm finishing the enigmatic dance. So now, we have the tool, we know how to look at it. So now, what I would like to present is the last bit, which I'm interested in most about, which are chiral molecules. So, it's all about chirality, right? I love chirality. So now, I have a question for you. Is this Taj Mahal building in India, is it chiral? And obviously, I hear you shouting to me, no, it's not, right? It's not chiral. Why? Because of symmetry. And we all see this beautiful reflection of the left side of the Taj Mahal onto the right side. So there is a mirror plane in the middle of the Taj Mahal. So let's try it now once more. So is this object chiral? And I again hear you shouting, it's not, right? Because again, symmetry. What is the symmetry here? So we see that if we pierce an axis through the middle of this orange lily, then we can rotate it by 120 degrees and it will be the same. So there is a rotation around axis. So maybe last time, so is this object chiral? Yeah, perfect. Now I hear you shouting yes. So the question is, why? So I'm going to kind of approach it the physicist way. So chirality basically means that something is missing. And that's interesting, right? So we will be looking into a mirror. Kind of thing I really love to do every single morning. So let's have a snail and let's have a mirror. So if the snail looks into a mirror, it sees its mirror image, right? So now, the important bit is this. The snail house, right, has some kind of spiral type of symmetry. So we go anti-clockwise, right? So that's this rule. And if you still remember from physics the right-handed rule, so if I kind of go this way, so something will be pointed out of the screen. So this is this arrow. So when this whole geometrical object looks into a mirror, it will see something like such. And the problem with chiral objects is this. If you do the same analysis here, so we are now going clockwise, and now if I am going clockwise, so my thumb goes to the board. So something is not adding up, and that means to be chiral. So in other words, if we have the object with the arrow pointing towards us, right? And here we have mirror image where the arrow points towards the wall. We see that they cannot be superimposed. It's like very much like your left and right hand, and therefore it also means that there is no reflection symmetry, right? No reflection symmetry means that we have to reflect this onto that, and that's not possible. So we know what and how to identify chiral stuff. So again, we are chemists, we should like molecules, they say. So is water molecule chiral? No, probably not, because I can easily find a plane which goes through the oxygen atom and this hydrogen sees that hydrogen, so there is no reflection. Also, I can pierce through some axis, and if I rotate 180 degrees, this hydrogen will be that hydrogen and vice versa. So that means it's a C2V point group symmetry, right? So it's too symmetric, no way to be chiral. But I can construct my molecule such that there will be no so-called improper axis of rotation Sn, and that object is going to be chiral. So this is multiple substituting methane, the simplest chiral molecule you can get. I love them because they are simple. And if it looks into a mirror, it looks good, right? But then, if we take the object, if we take the mirror image, we just realize they are not equal, so they are called enantiomers. So chiral molecules. Very good. So now, why do we care about chirality, right? Because like that something is there. Is it really justifying that we should study it? I'm not sure. So we care about chirality because there is a phenomenon called homochirality of life. That phenomenon simply means this: that we have L-amino acids. We only have these sugars. We have DNA double helix, which has one particular helicity, and that means that all the life interacts enantioselectively. And what my group wants to break is this. We are seeking a general probe of chiral dynamics in molecules. And for all that, we will need what I just introduced. So, in other words, we have to find an interaction with the chiral objects. But that's not easy, because, for example, the chiral object is this right-handed bolt, right? So if now I take this washer, which is an object which just doesn't have any thread, and I put it onto the bolt, and I will start rotating the bolt, let's say in this direction, the washer can either go this way or that way. There is no directionality. The same if I will turn the bolt in the other direction, it can go back and forth. So, that will not work. That means the washer, as a non-chiral object, will not see that this bolt is chiral. So let's try it better. Again, let's take right-handed bolt. And now, this time, let's take right-handed nut. And if I put it on and start to rotate it, so in this situation, it will go towards the head of the ball. In the opposite direction, it will go towards the tail of the ball. Beautiful. So I find some chiral-specific interactions. But you know, nuts and bolts, that's not too much good stuff for chemists. So can we do better? So can we get a chiral probe? Yes, we can. So we will try to kind of ask ourselves, so is light chiral? And the question is, yes, it can be made chiral. So say this is the line you kind of saw at the very beginning. I hope that now all of you also see there the magnetic wave, right? Just tiny, 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 tiny one. So this one, right? If we now look with this light and we will look how this electric field oscillates, so it oscillates in this perpendicular Y plane. So if such a called linear polarized light look into a mirror, it will see linear polarized light, therefore it's not chiral. So let's try a different polarization we have played. So for example, we can start with this circle polarized light, right? So this is this one. So now what we have to do is this. We have to look into the direction of incoming light. Please don't do that if you are working with lasers. Not good for your eyes. And we will see that these arrows go like, you know, this kind of anti-clockwise way. So such light is called left circular polarized light. If left circular polarized light looks into a mirror, sees this. Now that's definitely not right-handed circular polarized light. That means we have a chiral light. Hooray! We have the first part. We have the chiral probe for molecules. But I also said that I want a generator. So how to get the generator? So generator is, for me, photo-electron spectroscopy. Because all the selection rules you were kind of learning through your, I don't know, analytical chemistry courses, they are just relaxed and they don't apply. You can always photo-ionize if you just put enough energy into your system. So how we do it? So, for example, we have a pulse nozzle with our sample, be the water. Then we have a set of electrostatic lenses. They do work very nicely with those electrons we are ejecting. And then we have some position-sensitive detector. And such a device we call velocity bulk imaging spectrometer. Not really important for this talk. But what is important is that if you shine light in, and be it, for example, a femtosecond laser beam, then here we might cause this water molecule to get ionized. So then we eject some photoelectron, and that electron is by those lenses guided towards our position-sensitive detector. So now, if we will look at that detector, it might look something like such. We, in general, are looking onto an angular distribution of those photoelectrons. So that means, basically, here we have the water, and we are looking, if this is the light direction, where the electron goes. And those knobs, they are showing where there are a lot of electrons, and when there are no knobs, there are very little electrons. Perfect, so we have a tool which is very general. So now, can we combine it? Yes, we can. So we are going to get a general chiral optical method with photoelectrons, which we call photoelectron circular dichroism. So it works like such. Say we have a chiral molecule. Say we have a circular polarized light. Say this light is enough to eject a photoelectron. And what we will do, we will kind of imagine that there is a plane, mirror plane, which is perpendicular to the direction of our light. And then the plane which is behind we will call forward plane, and this one we will call backward plane. And then we will ask, where does the electron go? Into the forward or backward plane? So to answer that, we will measure our photoelectron angular distributions, right? And if we will do it, say, with left circular polarized light and this chiral molecule, we might have more electrons in the backward hemisphere. If we will do it with the right circular polarized light, we might have more electrons in this front hemisphere. And then we will do something you very well know, which is to calculate a Kuhn factor. Exactly like such, we will do subtract these two, and then we will normalize it, and then we are going to get our photoelectron circular dichroism signal. As simple as that. And now, finally, my presentation is going to culminate with catching the dance of chiral molecules. So how we do it? So we would like to have a variant of time-resolved PACD measurement. So which might look like such. Say I have again a chiral molecule, and I will shine light on it, which might be still well linearly polarized. And say this light is such that can, for example, dissociate this bond. So that it means this ball is going to depart slowly from the molecule, slower with respect to the pulse duration of my light, right? So then, later on, with some time delay, I can come up with a circular polarized light, and I can ionize this molecule, eject those electrons, do it with left and right in the polarized light, and get differences, which are those images. And like such, I have a tool to analyze the chiral dance of this molecule, which might look like such. So when this, say, hydrogen is going to depart from the molecule, the chiral signal will might swing into the enantiomer, which I'm going to get here. So with this, I'm going to finish my talk. I hope that I managed to illustrate that we need laser pulses to get time resolution, that we need laser pulses to see the dance of molecules, and that we need chiral molecules and chiral light to capture the dance of chiral molecules. Thank you.
I would like to thank Vít for a very interesting presentation. Now, if you have any questions, I have a microphone here, and I would like to ask you to tell the question to the microphone because we are recording the lecture. I didn't ask you before if you're okay with that, so if someone is here who doesn't want to be on the video, please just tell us and we will cut you. Okay, anyone has any questions?
Thank you. So my question is on your PowerPoint page 28. I'm curious of how do you make the molecule be aligned to a surface or a particular planary thing, make it like relatively stable, stable position to the incident light CPL pulse.
That's an interesting question. I don't, because I do not need it. The thing is that this works if the molecule will have whatever orientation in space you would like to have with respect to this pulse. It's not easy to see it right now, but if you go through all the math, you just realize that the signal we are measuring is still there, even if we average of all the possible orientation of molecules. So it's like we are always measuring the ensemble of molecules, which are randomly oriented. And
okay, and anisotropic.
Sorry?
Anisotropic.
And it's still small.
Oh, yeah. Okay. How about the second pulse arrive? The same molecule, exactly the same molecule, can change the position.
Yes, but the thing is that all the timescales we are looking into, right, which are, say, hundreds of femtoseconds, molecules will move basically nothing. Because obviously we are doing it with the light pulse. It means we are able, as I will show you here, to focus it to some area. This area to which we focus is not small with respect to the molecule size. And within this, let's say, hundreds of femtoseconds, with the speeds molecules are moving, which are hundreds of nanoseconds, we have years, a million of years of time to do so. So the molecules are literally fixed in space.
Okay, thank you very much.
Okay, anybody has any more questions? Okay.
Hi. So maybe I will ask. So, but still, you only ionize a certain percentage of. So that's also included in an ensemble and.
So on average, we ionize so we can ask everything. That's not the problem. But we generally excite just say with this very first pulse. We can excite, say, 5% of all the molecules. So obviously what we have to do is what we call a background saturation. So we always have some signal which is coming from the non-excited molecules, which are not doing the wanted dynamics, in this case will be the dissociation, right? But we have methods how to subtract that out from our signal. And the signal is strong enough on the order of tens of percents such that we can still see it.
From the baseline. Okay, thank you.
Okay, so I guess there are no questions at the moment, but I hope it will be staying later. So if you come up with a question later, please don't hesitate to ask. Okay, once again, thank you, Vít. Okay, so we are set. So please welcome the next member of VS Lab, Tomáš. He is also a UCT alumnus. He is a fresh postdoc in the VS Lab, and he specializes in poking molecules virtually before experimentalists poke them for real. His work ensures that we don't waste our time and resources on dead-end experiments. So before you shine your laser at a molecule, listen to Tomáš. He's already made a dance in silico.
Okay, thank you very much for the introduction. And I will very briefly introduce one of the projects and a little bit about computational chemistry. But right now, Petr Slavíček will be starting in 20 minutes and 15 minutes his talk about excrements in the library. So whoever wants to go, just go. We won't mind. It will be a great talk. Anyways, what is in silico chemistry? It's a play with words, and it just means chemistry which is done virtually on computers. It combines the power of theoretical physical concepts and the computational power of computers. What is it good for? Of course, we can do just theoretical calculations or simulations just for the calculations and simulations, and it can produce great results. But what is important for experimentalists, it can independently validate your experiments in your beakers, or help you to explain in more details what is happening there, because in our calculations and simulations we can achieve much higher resolution both in time and space than usually you can in experiments. Just a few examples what you can calculate with your computers. You can calculate energies of various molecules, you can calculate energies of different conformers that can help you to validate, for example, reaction mechanisms of organic reactions. If you are interested in dynamics, how the molecules move, what is happening in the beaker, you can run molecular dynamics simulations, and you can observe every atom moving, molecules vibrating and rotating, interacting with each other. And what is important for photochemistry, you can also calculate electronic levels and excitations, for example, of molecules. Computational in silico chemistry is relatively cheap because some chemicals are very, very expensive or even rare. You can't really get them easily. But again, I'm saying relatively cheap because the electricity isn't for free, the software can be also expensive, and the CPU hours can be also very expensive. The computational chemistry can be relatively fast in comparison to real experiments, but again, I'm saying relatively, some calculations or simulations can take hours, days, weeks, months. So again, it can be slow, and the computational chemistry is relatively safe. You know, computers are not really toxic, but again, the whole day sitting in front of computer isn't healthy also. Okay, and one of the projects we would like to study is the molecule of epichlorohydrin. It's a colorless toxic liquid, which is interesting for chemical industry, for example in pharmacy or explosives, but that's not why we are interested in it. We are interested in it because it's chiral. It can be into enantiomers, and we can photodissociate it. That means if we hit it with laser, it will fall apart, and we can study this process of dissociation. Okay, so if we want to study our epichlorohydrin, we have a sample of the liquid. In the machine, we will evaporate it, and then we have the epichlorohydrin molecules in gas phase, where we can hit it with the laser and measure some properties. But how does it look like in the gas phase? Epichlorohydrin isn't a really complex molecule, it's quite small, but still it can vibrate, rotate, it can change its configuration a little bit. And we would be, for example, interested how does the molecule look like in the gas phase. So we can run molecular dynamics, let the system, let the molecule evolve, and just observe how does it behave. But that may not be enough to sample the configurations of molecules, so you can help it a little bit and force it to some configurations which we are interested in. For example, force it to rotate, and we can calculate the energies along this rotation. And from this scan of energies during the rotation, we can identify that it has three minimas of some energies, and we can identify which geometry of the molecule corresponds to these energetic minimas, and therefore we can even calculate which is the most probable configuration of the studied molecule. So in this case, the vast majority of epichlorohydrin in gas phase will be in this configuration. And from this we can go on with our experiments and calculations. So as I said, we would like to photodissociate the molecule, and that we would like to clear the chlorine of the rest of the molecule. So if the chlorine is bound in the molecule, we need to add some energy to pull it apart. But we can do it in a smart way. We can hit it with a laser pulse, which can excite one of the non-bonding, one of the electrons in the non-bonding orbital to the antibonding orbital, which will get the whole molecule on this non-stable excited state. And you see there is no minima, so it's not stable geometric configuration, and it will propagate the movement or the configuration along this excited energy surface, which means that it will prolong the carbon-chlorine bond, and eventually it will break the bond. So it will photodissociate. Well, that's very nice. So we have a way how to break a bond, but that's not what we are after. We would like to study what is happening with the molecule during breaking this bond. And as was Vítek showing, we can do that by hitting the molecule during this process with another light, with another pulse. In this case, for example, with circular polarized light, and we can observe a signal what is happening, and we will get some signal. And we can hit the molecule at different stages of the photodissociation, and we will be getting different signals. And since the photoelectron circular dichorism is sensitive to the chirality, the chiral property of the molecule, we will learn something about what is happening with chiral molecule during the chemical reaction. I said that we will be hitting the molecule with the light, with the circular pulse at different times. However, I'm showing interaction along various carbon-chlorine distances. And again, this is example, because we don't have a good way how to measure the distance between the chlorine and carbon during the reaction. So that again, theory can help there. We can run the simulation in this excited state and observe how fast is the molecule dissociating during the process, and we can relate it to our experimental results to get more insight into the process. Well, and that was about this project.
Okay, so I would like to thank Tomáš for his short talk. Does anyone have any questions about the computing?
So do I get it right that you're doing excited state dynamics, excited state molecular dynamics?
I didn't have the results yet, but we are going to do this.
Yes, and what do you use for that? I mean, what software or?
Hopefully Orcam, and that's where I am right now.
Okay, thank you.
If you have the recommendation.
Thank you for the great talk. What about the Born-Oppenheimer approximation? Do you expect it to break? You said fast things, electron, surfaces merging.
I think this shouldn't be that fast. That this aspect shouldn't be a problem, and
Okay. So I had no experience in that fast things. So the question was if there is.
I should look into it to be sure it's okay, but again, the distillation should be at the scales of dynamics of molecules. Right?
Okay.
It's not super fast, but that's a very good question.
Thank you.
Thanks. Just a quick question. What was the selection for the epichlorohydrin? Because if you're studying the CCl bond dissociation, the chiral center is not changing.
Right, exactly. And as Vitek was showing before, molecules where you are changing the chiral centers were already studied, and so now we are moving further to more complex large molecules.
Sure. Okay. Thanks.
Okay, any more questions? Not for now. Okay, so with that, thank you, Tomáš.
Okay, so before you introduce me, I have some exercise for you, which will be relevant during my talk. And if you're interested, you can just take one fusilli per person, and I will tell you what to do with it later. Thank you.
Not a snack, so
Yeah, you can eat it, but it won't be delicious.
okay, so while the pasta is circulating, let me introduce our next speaker, Tereza Navrátilová is another member of the VS lab, and she will tell us about a technique called time-resolved photoelectron circular dichroism, TRPCD. Well, you now might be familiar with point chirality, but there are also, so to speak, higher order chiral molecules, such as DNA, helicenes, or the pasta you're getting. So how do we study chirality of this type? And can we manipulate it? Let's get enlightened by Tereza, from a postdoc from the VS lab.
Okay, thank you for the introduction. I would like to introduce you to some fascinating concepts that we want to study in our lab using PSCD or time-resolved PSCD that was previously introduced by my colleagues. So what you saw until now was PSCD made on simple chiral carbon. We call this chirality point chirality. And at this slide, you can see all of the molecules that have been measured by PSCD so far. And as you can see, most of them, more than half, were studies studying camphor or fenchon. And the other molecules are also quite simple. Why is that? It's because PSCD was developed and is mostly used by physicists. So they will obviously choose compounds that you can buy, that they are cheap, and you can just buy both enantiomers that have perfect properties, and they don't care about the structure. But we are chemists, so we want to study something much more complex. So let's forget about the chiral carbon for a while, and let's focus on some other elements, such as nitrogen or phosphorus or sulfur. I want to talk about nitrogen because these are interesting. Why? Because their enantiomers are mostly, or they don't have to be stable. So this molecule, it's ammonium salt, and you can get both enantiomers easily because these enantiomers are stable. But if you look at chiral amines, it's a different story. Why? Because their enantiomers can invert into one another by this process, which is called pyramidal inversion. And this process is pretty fast. We are in a realm of nanoseconds. And that's why we can't just buy a simple chiral amine, because it will change into its other enantiomer pretty fast. So this is interesting, and we can study it. As you can see, phosphorus and sulfur can do this inversion as well, but on much slower time rates. So their enantiomers can be obtained stable at even higher temperature, because the rate of the reaction is like the faster the reaction, the okay, I don't know, whatever. So, can we watch this inversion happen? Let's see. If we have just one molecule, let's say enantiomer E1, if we look at this molecule by common chiroptical methods, we will see racemic mixture, because we cannot distinguish this molecule in such a short time scale. But if we take our short laser pulse and we shine on our enantiomer, we can distinguish between the E1 and E2. So, but we can't measure just one molecule, and usually we as a chemist we work with a bulk, and so. So let's say we have one enantiomer, this E1, and we will shine a light on this enantiomer. We will excite it into some transition state, which will lose its chirality. It will be planar, and it can then turn into enantiomer E2, or in this case, I said it the other way around. It would be really interesting to study this process by time-resolved PSCD. But the problem is that we don't have this single enantiomer, because we cannot isolate it because of this fast inversion. And this is where Torger's base comes to play. So at this slide you can see a derivative of Torger's base. And Torger's bases are known and studied for decades, and they have a really nice history, because the first Torger's base, which is shown here, was the very first compound having chiral nitrogen that was enantio-separated. And it was done by Vladimir Prolog, who was awarded a Nobel Prize in chemistry in 1975 for his work on chiral compounds. So why are we interested in this particular molecule? It's because this methylene bridge helps us to fix the position of a chiral amine, so we can isolate this single enantiomer. So this is the perfect molecule to study the proposed inversion reaction. But to do so, we first have to break the bond again. And how do we do that? We will use our lovely light. Oh. So this is the project I'm currently working on. I want to study the photo-induced stereomutation reaction. What can you imagine by that is if we take one enantiomer of our Torger's base and we will use our laser pulse, we can break this methylene bridge, and it can rotate around this bond. And then, if we are lucky, it will close on the other side, and we will get the second enantiomer. Our PSCD signal then would look like something like such, that we have enantiomer E1 here, then we have some transition state which is not chiral, and then we will have the other enantiomer. Of course, this is not the only thing that can happen. What can also happen is that we will break the bond, but it will close on the same side again, and we will get enantiomer E1. If this competing process will be 50-50 probability, we will get photoracemization, and this is also really interesting to study. So in this case, we are losing our positive PSCD signal to 0 because we have racemic mixture. But there can also be some different equilibrium where we have a bigger probability that it will close on the E1 again, and then the PSCD signal would look like such. We have enantiomer E1, then we have then we break a bond, and then we get some positive PSCD again. So next, I would like to talk about chirality, which is not point chirality, because not all of the chiral compounds have a stereo center on the chiral atom. There are many different types of such chirality, such as axial chirality, which is based on the fact that there is some hindered rotation around the bond. My colleague will tell you how to prepare. Oh my god! How to prepare allenes, typical examples of axial chirality. Then we have helical chirality. I will talk about it on the next slides. Such compounds are compounds that are spirals, such as helicenes or nucleic acids. Then we have planar chirality, for example, this ferrocene complex, or topological or mechanical chirality, which is linked to the fact that you can have some molecular knots, and their chirality comes just from their topology. So we are interested in helicenes, and there are some people in the audience that are interested in helicenes as well. So what are helicenes? Helicenes are mostly aromatic compounds that are helical by nature. Well, you can imagine those molecules like a staircase, which can be go to the right or to the left. And here is a fun fact that I didn't know, but my colleagues told me a few days ago, that in the Middle Ages, at castles there were towers, and they had preferentially right-handed staircase, because defenders who were right-handed could have advantage. And so such as this staircase, helicenes also have this spirality. To describe this spirality or helicity, we use PM notation, where P is positive or clockwise or right-handed helicity, and the other one is M or minus or counterclockwise or left-handed. And this is where the pasta comes to play. I gave you a sample of pasta, and at the end of this talk, we can vote about if I handed you the P helicity or M helicity 1. So why are we interested in helicenes? It's because they exhibit a phenomenon called chiral-induced spin selectivity, or KISS. And what does it mean? The helicenes can filter electron spins based on their handedness. So if we have a pool of electrons which have positive half spin or the negative half spin, here they are differentiated by color. Based on the helicity of the molecule, one type can be preferred, and the other one will be blocked. So we obtain spin polarization. The important bit is that we don't need external magnetic field for that. So it can run on at room temperatures, and this can be used to create room temperature quantum computers in the future. And that's all from me. And after discussion, we can choose which fossili I gave you. To help you, here's the slide again, and thank you for your attention.
Okay, thanks a lot for the interesting talk. Are there any questions about the chirality, about different kinds of chirality?
Thank you. Hypothetical question, because I don't know BMI really that well. You always use linearly polarized, right? Light, or well, because I can imagine if you use CPL for the interaction, even any secondary amine, because you hit it at a particular moment in time, the secondary amine must be chiral at that moment in time. So you can have different interaction with different polarization of the light CPL. Is that correct?
Yes. So it depends on what you want to study.
Okay.
If you shine a circular polarized light onto this molecule and you don't have it oriented, then when you use, for example, left circular polarized light and you shine on the, let's see, E1 enantiomer from this side, then you will
Right.
you will see it
right.
as
the molecule is not oriented space.
Yeah.
Yes. Okay. Thanks.
So to use that, you would have to do orientation of the molecules in space, and that's something we want to focus on later as well.
Okay, I have a question myself, actually. I'm a layman in this, but you had the picture of the Traeger's base there. I'm just curious, you say you can break the bond there with light, so then it will just like fix itself after a while?
Yeah, the idea behind this is that we can use a laser pulse which will dissociate this bond exactly, and then by this mechanism, which is of course works only on paper, so we don't know if it will work, but it might. Then we will create such a bond that it can rotate and then close again by the same mechanism. Why we think it would work is because a similar mechanism was described in a solution where you can observe exactly this racemization.
Okay, I see. Because I was wondering, like, what's the probability that it will actually switch the chirality, and what's the probability that it will just snap back the same way?
But it would be interesting even to see that we can racemize the enantiomer.
Okay, thank you. Any other questions? If not, we can proceed with the voting.
Okay, so what do you think? How many people think that it's a... Wait, what's the first option? P helicity? No one? Okay, not anymore. So you're right, it's anticlockwise, it's M helicity. And so I explained it well. Thank you.
Okay, thank you. Before our final talk is presented, I actually want to make an advertisement for our next unicorn lecture, which will hopefully take place sometime in April or May. We already had the snails with their chiral houses, and now we were talking also about like right and left-handed staircase. But have you ever wondered why humans have kind of chiral bodies, why we have heart on the left side only? So we are hoping that we will get an expert on this kind of topic. So stay tuned for that. Okay, so I think we're almost set up. So let me introduce the last but not least member of the VS lab. And it's Tereza Pavlíčková. A short introduction. So, as we have seen, we have ways to study chiral molecules, but if we want to study the chiral molecules, we need the chiral molecules. That's kind of obvious, right? But, and we can buy some, but if we want to study them with the cutting edge techniques like TRP-ECD and others that have been introduced, we need really enantiopure chiral molecules, such as the allenes that will be introduced in this talk. And I found a funny quote on Wikipedia. And what does Wikipedia say about allenes? For many years, allenes were viewed as curiosities, but thought to be synthetically useless and difficult to prepare and work with. Well, who's useless now? Certainly not the allenes that Tereza is preparing. And besides preparing this useful stuff in her lab, Tereza also enjoys science communication, just like us in the Unicorn Club. And she also has experience with a Czech-French double degree, which she pursued in Montpellier. So if there are any soon-to-be PhD students, good time to ask her about that at the meet and greet. The floor is yours.
Okay, thank you for the introduction. So, hi everyone, I hope I will not exhaust you too much towards this end of the talk. But I would just like to give you a little bit of an overview how us organic chemists approach the issue of stereoselective synthesis, or more in general, how do we get one enantiomer out of the two when we want to study them by, let's say, laser pulses. Because for in silico studies, we don't care, you just have to draw it well, like here or in some better program. But if you want to do experiments, we need enantiopure molecules. So how do we, sorry, it's not working. No. How do we get only one out of the two? The story started actually many years ago with Louis Pasteur. I was a pharmacy student, and I mainly knew him for his studies about germs and his really breakthrough thoughts about germ theory. But Louis Pasteur was a chemist, and he realized that compared to the tartaric acid that he isolated from nature, which was dextrotatory, when he tried to prepare it in the lab, he was not getting any optical rotation until one day he started to look at the crystals of tartaric acid more closer up, and he realized that some of them, when he dissolved them, they actually were dextrorotatory, some of them were levorotatory, and when he looked at them under a microscope or magnifying glass, he could actually distinguish these crystals. So it's not only the molecules on microscopic level that were chiral and mirror images, but the crystals as well. And this was actually the discovery of the concept of molecular chirality, that he knew that these two molecules were mirror images just as the corresponding crystals. So this only applies to a very small range of molecules or compounds that crystallize in this way, so that are chiral and form chiral crystals, such as tartaric acid. But Louis Pasteur, so he could just crystallize tartaric acid and do like a Cinderella and just pick one crystal, other crystal, and separate them. But there are other compounds that are chiral and don't form chiral crystals, but they still can crystallize separately for each two enantiomers. So the crystal itself does not have a chiral form that you can just distinguish it from under microscope or with a magnifying glass, but there is a preference of R enantiomers crystallizing together and S enantiomers crystallizing together. So many years later, he came back to this issue and he again tried to crystallize some mixtures. And in this case, you just wait and then one enantiomer will crystallize and the other one will stay in solution. So you again solved your problem. You got a racemic mixture of enantiomers that you separate, you filter out crystals. The second enantiomer is in solution. But there is just 50% chance in this case that one or the other one will crash out. So what he did is what is obvious to us now, or maybe it is obvious to us, that he seeded the solution with one of the enantiomers, and then you can actually drive the process in one or the other direction. So these are kind of, let's say, primitive methods, but still work pretty well. So you have a racemic mixture, you can separate it by crystallization, but still limited to a small range of compounds. So there is roughly less than 10% of chiral compounds that can crystallize in this way. Most of them would just form racemic conglomerates. So there is no preference over R or S in crystallization. You cannot use this method. And for this, we have more advanced techniques now. So we still can separate racemic mixtures by using, for example, chiral HPLC. So for you who have been here a couple of months ago for Professor Coates' lecture, he talked a lot about this. So I will not spend this much time. But if you pass a racemic mixture through a chiral stationary phase or through a column that is packed with silica that is modified with some sort of chiral moiety, there will be likely some preference for one of the other enantiomer to stay on the column and the other one to get flushed out. So, for example, the S might like the S better, and then the R will get out of your column first, then followed by the S enantiomer, and so on. It can be the other way around, but if you are lucky enough, you can separate your mixture this way. This is one example of a stationary phase that is being used, so you can use something like this chiral amine, modified silica, or what is very common, some sugar-based moieties. Then the separation is based on some weak, let's say, or non-bonding interactions, such as hydrogen bonding or pi interactions. That's why we have also these aromatics here. And luckily for us, this works for quite a range of compounds. And you can maybe here, if you look like close enough, you can recognize the Traeger's base structural pattern inside. So this stationary phase can be used to separate these compounds. Here we have the famous helicene structure, and this also works for some other molecules, which are the chiral allenes that I also am interested in and will talk about more. We are chemists, and I am an organic chemist, not an analytical chemist, so I like to use chemical reactions to introduce asymmetry into the molecule. And we can still start with a racemic mixture, but we will use this time chemistry to separate the enantiomers based on the process called kinetic resolution. So we have a chiral reagent, chiral catalyst, or something that will recognize one of the enantiomers, or it will bind better to one of the enantiomers, or after binding them, it will bind the other substrate faster. So overall, the reaction with one of them will be favored. So only one of them will be transformed and react, and the other one will remain untouched. So this is a pretty popular process for example, for synthesizing such chiral alcohols, when you can take cheap racemic mixtures and use a chiral selector, in this case a copper catalyst. You do a click reaction, and then you have two separate products. One is unreacted alcohol, and the other one will be the product of the famous click reaction. And you can use it for different type of chemistry. Depends on whether you are interested in this one or that one. A lot of the time use enzymes to do this sort of resolution. So typically we can use lipase to acylate on this alcohol. And in this case, again, one enantiomer remains unreacted and the other one will be acylated. Again, pick whatever you need from the mixture. Thing is that the kind of overall yield of this process will only be kind of 50% because the starting point is already 50%. But we, in this case, can use these chiral alcohols and transform them through a couple of steps to our chiral allenes. And here I will just like to stop for a little bit to introduce the chirality in these allenes, because it might not be that intuitive that these are actually enantiomers and they only have one stereogenic element. This is not something like, there cannot be like a double bond isomerism. They are actually enantiomers, and we can see it better if you look at them from like here, from the same way we would look from the top to the alcohol. We can look from this side to the allene, and we see that they are kind of oriented around this central axis, and there will be two planes that are perpendicular to each other. You can see it maybe better in this picture. So this is this does not have at all like alkene geometry. This center bond is linear and they are oriented perpendicular around each other. And you can also see that in this case, if you exchange these two residues, like you would do, for example, here, and then you try to superimpose, you see that you actually get the mirror image. So they are indeed enantiomers. Chemistry, resolution. What if we want to make complex molecules and we want to take inspiration from nature? Nature gives us a lot of chiral molecules for free that we can extract for, okay, not for free, but for cheap. We can extract from the materials that we have. Let's see, we can extract such a drug, paclitaxel, which is a cytotoxic compound, but not in a very high efficiency. So we can still look at it, and let's think it has 11 stereocenters. We have this pool of chiral compounds available for us for not so much money. Can we use some of them to synthesize this compound more efficiently? Yes. That's what we do usually. So I don't know if any of you can see the pattern. It's not that easy, but maybe some of you can see this terpene molecule here, and this was actually used for synthesis of paclitaxel. Not, I don't know now in how many steps, probably a lot, but still it was way more efficient than to extract it from nature by itself. And there is another option if you take this whole bicyclic skeleton. Again, this is, I think, patchoulin. You can start from patchoulin, and again, in a few steps, you make paclitaxel. So nature offers us chirality, but we want to still do more and start with something that is not chiral at all. So we take prochiral elements, which are molecules that either don't either are planar or linear, let's say, or they are symmetrical. So then we need chiral reagents or catalysts to introduce the asymmetry and the three-dimensional information. This is what enantioselective synthesis does, and this is kind of the pinnacle of chemistry. So we can then choose if we want to make S or R enantiomer based on the reagents or catalysts that we use. And I will just show you some nice examples or typical examples. So this is the case where you have a prochiral molecule that is three-dimensional, so it is sp3 hybridized carbon, but it is symmetrical, so it just has two hydrogen atoms. In this way, we distinguish which one of them will be deprotonated, and then we alkylate on one side only. And this moiety, this chiral, not catalyst but reagent in this case, is then cleaved and does not remain in the final molecule. So this is one example. Another one is from the planar element. We can selectively hydrogenate from one phase or the other and get chiral alcohol. This is one of the most efficient ways of getting chiral alcohols. Or this is my very favorite, and I hope that some of the there are some organic chemists in the audience that can appreciate the beauty of this transformation, which is a three-component reaction where we have when we have two prochiral elements, one linear, one planar. We have a helicene, or like, okay, let's say axial chiral catalyst, and then we construct something that is an alene, so axial chiral molecule with an additional stereocenter. So this is beautiful transformation. I can show you how it works maybe later, but now for the sake of time, I will just go to close up my talk. And I think I convinced you that chemistry has a lot of tools to build chiral molecules or enantiomers. So we can start with crystallization. We can start from racemic mixture and separate it or resolve it using chiral enzymes or catalysts. We can use the chiral pool method where we use what nature gives us and just transform it. Or we start with something that is not chiral and use, again, chiral catalysts, reagents to make it chiral. But there is a catch in all this, because chemistry is actually pretty weak. Do you see that we generate de novo chirality or asymmetry? We actually don't. We don't, in neither of the cases, we don't break symmetry, because everywhere we add some external element that is already asymmetric. Here, if we want to steer it one way, here we need chiral elements to construct chiral HPLC phase. We need chiral catalysts, we need chiral reagents. So we didn't actually achieve all that much, although it is impressive. So can we at all break the symmetry, and how nature does it in a way? How does nature construct the chiral pool, and why is it homochiral? And this is where I circle back all the way to the beginning and to what Vitek was talking about, where it all comes to the chiral light. We can actually make circularly polarized light by using non-chiral elements only. So we just need a quartz crystal that will be rotating, and it will cause the plane of polarization of the linearly polarized light to rotate. We will generate chiral light, and this is also a hypothesis of what nature kind of does. That at the very beginning there is circularly polarized light that interacts with matter, and then the rest is all chemistry, but in the beginning, the first asymmetry is caused by electromagnetic radiation. So the chemists cannot play God, and we cannot break the symmetry, but apparently physicists can. So let there be light, and let there be chiral light, and with that thought, I leave you, and I'm open to answer any questions.
Okay, thank you, Tereza, for the very interesting talk. So, are there any questions about the synthesis of chiral compounds, molecules? So maybe not for now. I'm thinking if I have any question by myself, but as you said, like, we can do almost anything.
Yeah, almost.
So what are the things that are left to discover regarding the synthesis of chiral molecules?
Well, that's it's a very philosophical question, but I actually believe that these days chemists can really do anything, and the question is now more about making it more efficient, making it green. That's a big question. So replacing all the expensive transition metals that you use in catalysis by the cheaper ones, and I don't think there is like a big unanswered question in organic synthesis, really. So that's why we switch topics and go where the big question still remains to be answered. Yeah.
Okay, any more questions? Looks like not for now. So everyone, I invite you to give your hands together for Tereza. And now it's time for you to go stretch your legs, and me and my team here will prepare some refreshments for you. Thank you so much for being here with us today, and I hope to see you soon on other unicorn parties. Thank you.